Hello everyone, and welcome to today's session on predictive maintenance with MATLAB. My name is Adam Fillion, and I'm an application engineer at the MathWorks. In today's session, we're going to take a look at how we can monitor the health of our equipment and forecast when to do maintenance so that we can avoid unexpected failures. Before we begin, I have a few logistical details for you. If you have any problems seeing or hearing today's webinar, please enter those in the chat tab and the webinar host will help you sort through them. If you have any technical questions on the content of today's presentation, please enter those in the Q&A panel at any time. At the end of the presentation, we will go offline for a few moments, compile those, and then come back online and answer as many as we have time for. I'd like to start today by showing you a quick example of what can happen if we don't get our maintenance right. So what we have here are some electricity generating wind turbines, and one of them is about to have a problem. Let's take a look at that again. So what happened here is there's a braking system in the turbine to keep the blades from spinning too fast during a high wind situation. The braking system had a failure. And during a storm, the blades spun so fast, you can see it right here, that they actually tore themselves apart from the rotational forces. This shifted the center of mass, and the result blew this turbine apart. Obviously, this was a huge problem. Wind turbines cost millions of dollars to build and install, but even more so, these types of failures can be very dangerous. Debris was actually found half a mile away from the site of the explosion. Fortunately, in this case, nobody was hurt, but there was a very real risk of damage to people and property. And the main suspect behind the cause of this was that maintenance had not been done often enough. So you might ask, well, why don't we just do more maintenance? Unfortunately, it's not that simple. Not only is maintenance itself very expensive, but it can actually be dangerous for the maintenance crews. These wind turbines can be very tall. The ones you were looking at in that video were 70 meters off the ground. So we have to find some way to get our crews up there. Sometimes we even have to drop them on top from a helicopter. And if this is an offshore wind farm where they're installed out in the ocean, then all of this gets even more complicated because now we have to balance on top of a boat that is moving and bobbing in the water. So how can we build some kind of system so that we can both avoid these potentially dangerous failures and also not have to do maintenance too often? Well, we'll take one quick look at something that we could build in MATLAB. So this is just a simple desktop app that we built for monitoring a jet engine. We've got a number of different sensors reading data off of this engine while it's running. And then behind the scenes, we have a machine learning model that we've trained to understand how far away is this piece of equipment from having a failure. In this case, we're bucketing it into a couple of different groups. Does this have a really long time until failure, medium, short, or is this about to have a failure and really urgently in need of maintenance? And so you can see right here, it joins the urgent region. So we can automate having alarms sent out to different people once that happens. And then at the last data point here, this is where this particular piece of equipment actually had a failure. So we're not going to focus on building graphical front ends today. We're really going to focus on how we can use MATLAB to build the analytics necessary to understand this type of sensor data, to make some forecasts about the health of our equipment and when to do maintenance. And then how can we take that and integrate it with the equipment itself in larger enterprise systems? Before we get into that, I want to take one quick step back to talk about some of the different ways or styles of doing maintenance and why we really want to do predictive maintenance. Now, one way of doing maintenance is by being what we call reactive. Basically, we're doing maintenance once there's a problem. And an everyday example of this is your car battery. I don't know anyone who even thinks about their car battery until it has a problem, at which point we usually just replace it. Now, the main problem with being reactive is that you run the risk of having a lot of unexpected failures, which can be very expensive and potentially dangerous. So what most people do instead is scheduled maintenance, where we do maintenance at a regular rate. And an everyday example is the advice that we change our car's oil every 5,000 miles. However, if you're doing maintenance on all your equipment at a set rate, regardless of its actual condition, then I can pretty much guarantee you that some of that maintenance is going to be unnecessary, meaning that it's wasteful. And even so, you may not eliminate all failures. So what many people are now trying to do instead is predictive maintenance, where we forecast when problems will arise ahead of time. There's many people trying to do this. Just one example is General Motors now has some car models where the car will actually monitor the battery, fuel pump, and starter motor, and can even email the driver with recommendations on when to perform maintenance. So this is an example of how we can not only do predictive maintenance for ourselves, but it can even potentially be a service that we provide to others. However, predictive maintenance isn't without its own difficulties, namely that it can be very difficult to make accurate forecasts for complex equipment. So this is really what we're going to try to tackle today, because if we can get this right, the potential benefits are huge. We can increase the uptime, the availability, and also the safety of our equipment. We can minimize the maintenance costs. And we can also optimize our supply chain, because if I know what type of maintenance I need to do and when and where, I can make sure that all the right parts are going to be at the right place at the right time. And what this really leads to is increased reliability of our equipment, a lower cost of ownership for the operators, and a better reputation for our organization and our products. So these are the goals that we're really chasing today. So who's really doing this? What does success look like? I always like to share at least one example of someone who's using MATLAB to do this in the real world. And one organization is SNECMA. So SNECMA is one of the world's leading manufacturers of commercial jet engines, and they use MATLAB as a central part of their monitoring system. They monitor many different parts of the engine to try to detect failures ahead of time and predict how long until maintenance is needed. They do this with two main goals in mind. One of them is to improve aircraft availability, such as on-time departures and arrivals, and the other is to reduce maintenance costs. And they use MATLAB throughout this workflow. They started on the desktop doing ad hoc analysis, sort of like we're going to do today. Then they took their MATLAB applications and they compiled them so they can share them with their colleagues. And then eventually took their MATLAB application and integrated it into this larger enterprise system. They gave a great presentation at our MATLAB virtual conference in 2015. So if you would like to see a talk done by them on how they integrate MATLAB into their large real-world system, you can actually go on our website and watch that at any time. What we're going to do today is we're going to focus on a similar example. So we have some data provided by NASA, this is public data, and this is sensor data coming from 100 different turbofan jet engines of the same model. So these engines have different parts, and we have various sensors throughout the engine measuring things like temperatures, pressures, rotational speeds, and so on. However, if you don't know anything about jet engines, don't worry, you don't need to. We're not doing anything today that is specific to them. We're going to treat this sort of like a black box piece of equipment that just has some sensor data coming out of it. So the workflow we'll go through, we're going to look at quickly importing and visualizing the sensor data. We're going to train some machine learning models to try to understand its condition and predict when we should be able to do maintenance. And then we'll talk about how we can take what we've done and deploy it to run on live sensor data, either in some kind of server or cloud infrastructure or on the actual piece of equipment itself. And we'll look at this in the context of two different scenarios. So the first scenario we're going to look at is when we don't have any data from failures. And failure really just means whenever my equipment starts doing something I don't want it to do. This could be something more catastrophic, like in the wind turbine example we saw earlier. But for our data set today, it really just means the aircraft equivalent of your car's check engine light turning on unexpectedly. That's the kind of failures we're talking about today. So when we don't have any data from failures, typically the situation is we're performing scheduled maintenance, and we're performing it often enough that we haven't had any failures happen. So that's good. But again, if you're doing scheduled maintenance this often, I can almost guarantee you that if you go talk to your maintenance crews, they're going to tell you that many, if not most of your engines could run for longer without having maintenance done on them. So the question is, can we be smarter about how to schedule our maintenance without knowing what failures actually look like in the data? So this is going to be the first scenario we're going to look at today. Let's go ahead and hop over to MATLAB. So I've got a couple of scripts here to help us walk through our examples today. You notice here that I'm using what's called a live script. This is something new in the 2016A release of MATLAB. It gives me a single place to organize not just code, but richly formatted text, images, equations, plots and outputs, and so on. And if you're interested in learning more, I encourage you to check out the website. We're going to start today by just reading in and visualizing the data from one engine. I always encourage people to start small, prototype, and then build up from there. So I've got engine data from one engine sitting in a CSV file in my current directory. So we're just going to read that into a table. So if we look at our workspace, you can see we've got a table of data here that we've read into MATLAB. I can see which engine this is. We have a timestamp. In this case, the timestamp is a flight. So each data point is a flight, and you can think of all the different sensors as sort of like a summary statistic of what happened during that flight. But we're not doing anything specific to that way of measuring time. You can think of this as just any kind of generic time step. And then we've got a number of different sensors throughout the engine. We've got 21 in total. So the first thing I always like to do when I get some new data is to make a plot of it, to visualize it. Now we've got 21 sensors in this case. That's a bit much to put up on the screen at one time. So let's make a quick subplot of the first 9 sensors. And you notice I can have this plot either pulled out to the right or actually inline it with my live script along with all the text and code. Here, I'll keep it over to the right. And you can see that some of these sensors are actually constant throughout. From 0, which is our first timestamp where we started recording the data, all the way until the 125th flight. So that was the pace of the scheduled maintenance in this case. We started using it, and after 125 flights, we took it offline to do maintenance. Some of these sensors are constant throughout, and if they're constant and never change, well, they're probably not too useful for understanding what's the condition of this piece of equipment, so we probably want to throw those out. Some of the other sensors, they are changing over time, but they look a little noisy, and in fact, if you go read the paper that NASA published along with the dataset, you know that these do have a little bit of random noise with them that we probably want to smooth out. So we'll start by just picking out the variables from our table that we want to keep. And we'll use a simple moving average, trailing moving average, to smooth out some of the data. And so now let's take a look at the result. So you see here on top, this was kind of the original data. So we threw out these constant sensors, and then the other sensors we smoothed out a bit. So obviously there's a lot of pre-processing work that we can do in MATLAB. MATLAB's very powerful for that. But let's say that this is enough for what we're doing today. The question now becomes, how can we use these sensor signals to help us understand what's the current state of our equipment, and how can we use them to help us make better decisions about maintenance without knowing what failures actually look like? Well, one of the traditional ways of monitoring this type of equipment is using something called a control chart. Now, in a control chart, we have a center line. This is ideally what we would like our data to be at. We have upper and lower control limits, which is the limits for what our sensor data should stay within. And then if our sensor over time, if it goes outside of that, well, we might mark that as a potential problem. And if you have a small number of sensors and you have a good idea for how to set these upper and lower control limits, then this might work just fine. But for us today, once we throw out the constant value sensors, we have 14 different sensors that are left. That means we would have to have 14 different control charts to set up and monitor. We also don't have a good idea for how to set these upper and lower control limits. So to help us with our problem today, I'm going to briefly introduce one class of modeling called machine learning. So machine learning has become very, very popular for a certain class of problems, namely problems that have too many variables to easily understand. In this case, we have 14 sensors right now. I certainly consider that to be too many. And our system is too complex to know the governing equation. So I can't sit down from first principles like Newton's second law and derive out an equation that describes how this thing is going to behave. And you see examples of machine learning coming up everywhere. In speech recognition, in image recognition, such as tagging faces, in financial analysis, and certainly lots of places in engineering. Machine learning can be broadly split up into two different subgroups, what's called supervised learning and unsupervised learning. Supervised learning is all focused around predictive modeling, around making forecasts. So the idea here is we have a historical record of both inputs and outputs. The inputs is going to be what's readily available to us. For us, that's the sensors we get off of our engine. We also need a historical record of outputs of correct answers. And this is important because if we have correct answers, then we can supervise our model while it learns. So it can see for this type of input, I need to give this type of output, and for this different type of input, I need to give this different type of output. In our example, the output would be data from failures. And we don't actually have that right now. We'll look at it a little later. But for the scenario we're currently in, if we don't have data from failures, then we can't actually use supervised learning. We have to use the other kind, what's called unsupervised learning. So in unsupervised learning, we're actually not trying to forecast anything. What we're doing is we're looking at the natural structure of the data to see if there's any sort of groupings or interpretations that we can make to inform us about our system. And so this is what we're going to start with today. Now, there's many different types of unsupervised learning out there. We're going to look at just one of the more common ones, which is called principal components analysis. So principal components analysis tries to summarize as much information as possible on a lower dimensional set. So it's trying to reduce the number of dimensions that we need to work with. Let's consider a simpler three-dimensional problem here where we have this sort of cigar-shaped cloud of data points. The first thing principal components analysis does is it asks what straight line drawn through the origin will explain the maximum amount of variance or spread in the data. So we'll get something like this, and this is called the first principal component. By moving along this straight line, I can explain more of the data than by moving along any other straight line. But we haven't explained everything, so the next step is to ask what straight line orthogonal to my first principal component will explain the maximum amount of variance that's left. And so we might get something like this. And so what this really gives me is a new set of coordinates, a new set of axes in which I can measure and visualize my data. So I think of this as rotating my axes such that they point in the directions in which the data varies the most, and that will then let me summarize as much information as possible in a smaller number of dimensions. So let's take a look at how we could do this in MATLAB. Now there's two things we're going to do first. One is we're going to read in all the available data that we have. So right now we were looking at just one particular engine, but we actually have 100 different engines organized in this folder here. And I'd like to read all 100 of them in. And we're going to use something called a data store. So this gives me a really easy way to read in data from multiple files. It even has tools to help me if the data is too big to all fit into memory at once. But for today, it will all fit. So we'll use a simple read all command to read all the data from the data store into MATLAB. And now that we've read all the data in and reapplied the smoothing to get rid of the noise, now you can see the result. And now you can see this is all 100 engines plotted on top of each other. And now there actually isn't really any clear signal here. There's really just kind of a range, just kind of a bar moving through time. And this is one of the things that the principal components analysis is going to help us to understand. The other thing we need to do is we need to standardize our data. So our sensors are being measured in different scales and in different units. So some of these are measuring temperature, some are measuring pressures, some are dimensionless ratios. And principal components analysis involves measuring the distances between data points. So in order for those distances to make sense, we need to put these sensors on an equal footing somehow. Now, there's many different ways to standardize or normalize data. It really depends on the characteristics of your data and the type of analysis that you want to do. In this particular example, our signals are fairly close to normal in the normal distribution sense of the word. So we're going to give all of them a mean of 0 and standard deviation of 1. But again, there's many different ways to do this. It really all depends. All right, so now that we've read in all the data and we've standardized it, now we're ready to go and perform our principal components analysis. So it's a very simple function in MATLAB, just PCA on our sensor data. And we'll take a look at two different plots. So this first plot here, this is showing us how much the principal components are explaining. So in orange, this is the individual principal component. And you see the first principal component actually explains over 75% of the total variance in the data. So even though I have 14 sensors, I have a 14-dimensional data set, I can explain over 75% of its variance with just a single straight line drawn through the origin. The second principal component can explain about another 11%. And if I add the two of them together, cumulatively, they can combine to explain almost 90%, meaning that even though I have a 14-dimensional data set, I can explain almost 90% of its variance with a two-dimensional plane. And this is what that data projected into the two-dimensional plane looks like. So this is all the data points from all 100 engines. Only now, instead of plotting them in terms of the original raw sensors, now we're plotting it in terms of the first and second principal component. And so here we can see that it looks like we have maybe one big cloud of data points that are all pretty densely packed, but we also have some data points that wander pretty far away from it. So from this, we might take our first initial guess. We might form a hypothesis that we have a lot of engines running for a long time, and we know that most of them are in normal conditions most of the time. So this cloud of densely packed data points might represent normal behavior. However, we also know that some of the engines, as they approached their scheduled maintenance date, started to deteriorate a bit. And when our maintenance crews got out there, they noted that some of the engines were badly in need of maintenance. So some of these points that wander away from this central group, those might represent engines that were starting to deteriorate and were in need of maintenance. So let's say that's our initial guess. What can we do to investigate this? Well, the first thing we might do is just make a kind of a simple plot, looking at the first and last data points for each engine. So what we're looking at here, in blue down here, this is the first data point for each engine. So the engines are running, we start recording data, and in blue is the first data point that we get off of each of them. And you notice that they all reside in that densely packed region. The red data points is the last data point we took from each engine before its scheduled maintenance date. Some of them overlap, and that's actually to be expected. If some of our engines are perfectly fine in normal conditions at the point when scheduled maintenance was performed, then I would expect them to overlap with the first data points from when we first started recording. Some of the other data points were very far away from where they started by the end. So this might give us our first impression that it looks like maybe as engines deteriorate and move away from normal conditions, they might generally move in this direction in this principal components plot. Next, we might want to take a look at just the problematic engines. So many of the engines were fine at the time of scheduled maintenance, but some of them were actually badly in need of maintenance. And our maintenance crews actually identified 4 of them as being in particularly bad need. So here we'll take a look at just what do the last 20 flights from each of those engines look like. So those are the ones that we've highlighted here in red. And so you can see that those are definitely the ones that are wandering the furthest away from this big cloud of data points. And we can even look at how these different engines evolved over time. And so what we're looking at here, this is the path that a particular engine, engine 39, took through the principal components plot while it was running. So it started at this yellow point. This was the first data point. It wiggled around here in the normal region for a while, and then started to move away from it, first slowly, and then more quickly towards the end. And then this red data point here, this is the last data point prior to maintenance. So using what we've learned here, we might take our first initial guess as some criteria to determine when a piece of equipment is transitioning from normal conditions to something else. And our first guess might look something like this. So our big cloud of data points, we might consider this to be normal conditions. So this is the green area we've outlined here. And as long as we're inside of here, everything's fine, nothing to worry about. if we start to wander outside of this region into this yellowish-orangish region, well, then we might say, well, it's no longer normal, but it's not in really bad shape yet, so maybe we want to issue some kind of warning to keep an eye on this piece of equipment, or maybe prioritize it to have maintenance soon. If it wanders into the red alarm region, then this might mean that the engine has really started to deteriorate badly, and we need to make sure that we do maintenance very quickly. So I think of this as a two-dimensional version of the control chart that we looked at earlier. But now, rather than plotting our data points relative to their raw signal values, now we're projecting them into this principal components plot. But then how can we take this and implement it when we still don't actually know what failure looks like in the data? Well, there's no one right answer. There's lots of different ways to do it. But I'd like to quickly sketch out just one idea for how we might implement this. So you can think of the data that we got as coming from round one. We have a series of engines, we started running them, we were recording data, and after 125 flights, we went ahead and we performed our scheduled maintenance. We then took this data, we brought it into MATLAB, we analyzed it, we developed our criteria. Now these same engines, after having maintenance performed, are going to start running on round two. As they run, we can monitor them to see are they in the normal warning or alarm regions. Now it's up to us to decide, based on this feedback, when might we want to do maintenance. So for example, we might say, well, if it goes outside of the normal region into the warning for a couple of data points in a row, then we might want to go ahead and prioritize doing maintenance on it. Otherwise, as long as it's normal, then it should be fine. But if this is the very first time that we're doing this, then we probably don't want to let them just run forever. So we might still be doing scheduled maintenance, but we'll push back the pace of it. Instead of 125 flights, maybe 135 flights for round two. We'll take all this sensor data, we'll take the feedback from the maintenance crews, and we'll use it to evolve our criteria, to update our models for what is normal, what is not normal, and when does it transition from one to the other. Then as we get into subsequent rounds, like round three, some of our engines might not last too long, other ones might keep running, and so over time we can continue to push back the pace of this regularly scheduled maintenance until we get to a point where we're not doing any scheduled maintenance at all, and we're only scheduling our maintenance based on this type of criteria. And along the way, we'll gather more data, we'll gather more feedback from our maintenance crews, and we'll continue to evolve this. As our initial guess, we made some rectangles here, but odds are it's probably not a perfect rectangle. It might be circular, it might be irregular, and so on. So if this was really the case, if we really didn't have any data from failures, then we might have to stop at this point and go implement something similar to what I just described. But we've been a little bit misleading. We do actually have data for each of these engines running it all the way until it hit failure conditions. We were just ignoring what happened after flight 125 so that we could look at this type of scenario where we don't have any failure data. So this is a little bit like cheating, but since we do have data for running it all the way to failure, let's see what would have happened if we had held these conditions constant and let all the engines run until they failed. So what we're looking at in this plot here is all 100 engines run till failure. They're synchronized so that they fail at time 0. And these negative values down here, these are flights prior to failure. Along the y-axis is the fraction of the engines that are currently in normal warning or alarm conditions. So you can see that this starts over 350 flights prior to failure. So at least some of these engines ran for over 350 flights prior to hitting failure conditions, so we lost a lot of availability by doing maintenance after only 125 flights. Around 150 flights prior to failure, some of the engines started to wander outside of the normal region and into the warning region. Around 75 flights prior to failure, some of them started getting into the alarm region. By around 25 flights prior to failure, all of them had left the normal region. None of them were in normal conditions anymore. And by the time we got to 9 flights prior to failure, all of them had entered the alarm region. So every single engine would have generated an alarm for at least 9 consecutive flights prior to failure. And so there's a lot that we can learn from this type of plot. Now, I think a lot of people, ideally, would like to see these transitions from one state to the next all happen at once. So maybe, for example, at 100 flights prior to failure, all of the engines all at once would move from the normal to the warning conditions. But that's not what we see. And there's 2 potential causes for that. Number 1 is this is using our initial guess for what the conditions should be for normal and warning and so on. And those certainly could be improved. But another possibility is that this represents what's really going on. Some of the engines start to deteriorate fairly early on, but do so at a slow rate, and it takes them a long time to hit failure. Whereas other ones might be totally fine all the way up to the very end and then very quickly transition from normal conditions into failure. And so looking at this type of analysis, we can analyze which engines are which, pull them aside, and look at them to see if there's any conclusions we can draw from that. Finally, we might want to ask, well, how much uptime did we really gain? Well, that depends on exactly how we're going to do our maintenance. But for example, if we did maintenance upon the first warning condition, we might gain a little bit additional uptime. This is versus doing it as a scheduled maintenance. If we did it upon the first alarm signal, we'll gain some more. And then there's the maximum amount that we could gain by doing maintenance 1 sample before failure. So this is like perfect foresight. Now, if you've done this type of work before, these numbers might look a little unrealistic. It turns out that NASA curated this data so that it started fairly close to failure. However, the trend tends to hold true, that there's usually a more conservative implementation that might only gain us a little bit over our scheduled maintenance. There's a more aggressive one that can get us more, but it's a bit riskier. And then there's the maximum amount that we could possibly get if we had perfect foresight. So in this first scenario, we were looking at what could we do if we don't have any data from failures. But as I just mentioned, we actually do have data for failures in this data set. So let's take a look at what we could do now that we have failure data. So this is going to be our second scenario for today, when we actually have data from failures. Now, when this happens, typically we're not being reactive. We are performing scheduled maintenance. But failures are still occurring, and this may actually be by design. We may find that in order to eliminate all failures, we have to do scheduled maintenance at an unrealistic rate. So we can search our records for when the failures occurred and gather the data that preceded those failure events. And the question now is, can we predict how long we have until failures occur now that we have this data from failures? So this puts us into the supervised learning region. Now that I have both inputs and outputs, now I can make some forecasts. Supervised learning has 2 main subcategories, regression and classification. Regression is where the output is continuous. So this could be something like power or distance or time. In our example, a regression approach would try to predict exactly how long we have until failure. Classification is a little bit different. In classification, our output comes from a small, discrete set. So the output could be binary. It could be yes or no. Will this piece of equipment fail in the next 10 cycles? Or the output could come from maybe a couple different choices. Is this piece of equipment urgently in need of maintenance? Or does it have a short or medium or long time until failure? Both regression and classification are valid approaches. Both are used in the industry. Each one has its own set of pros and cons for and against it. For the sake of time today, we're just going to look at one of them. We're going to look at classification. I also want to make one quick note on how this data was recorded. So for each engine, it was actually run for an unknown amount of time prior to when the data recording started. So some unknown amount of time after initial use of prior maintenance, but still in normal conditions, we started recording. This went for a while until it hit the failure conditions. Engine 2, different unknown amount of time after initial use of prior maintenance, we started recording all the way through engine 100. And so now that we have all this data running all the way until failure, If I get a new engine, the goal is now I want to be able to start recording and then stop at any moment and make a forecast so that I can smartly plan out my maintenance. So let's hop back over to MATLAB and take a look at our classification problem. Now, earlier we looked at importing data into MATLAB, visualizing it, cleaning it up. Since we've already done that, we're going to skip that and just load in some data. Now, if we want to perform classification, we need to set up the classes. What are the buckets we're going to try to predict each data point belongs in? And there's no one right way to determine what classes you should use. For us today, we're going to use 4 of them. So if something is really close to failing, we're going to say that's urgent. And then to help us with longer-term planning, we're also going to create buckets for engines that have a short, medium, or long time until failure. Now, an important point is, where do you draw the boundaries between these different buckets? When does it transition from one to the other? And this is something we actually can't determine purely from the sensor data. Usually we have to go talk with some other groups, like maybe our maintenance workers, and ask them, if I tell you you need to do maintenance in the next 3 flights, is that easy to do? Does this deserve an urgent rating? And so on. For us today, we drew just a couple arbitrary boundaries between these different buckets. So for example, if something is within 50 flights of failing, we'll call it urgent. If it's outside 50 flights but before 125, we'll call it short, and so on. And so now let's take a look at all of our data running all the way till failure and what these different buckets look like. So here we're looking at, again, this is 9 of the sensors coming off of this particular engine. All 100 engines are plotted here. They've all been synchronized so that they all fail at time 0. And these negative values are flights prior to failure. And you can see these different colors. These are the different classes that we have that we're going to try to predict for each data point, which one does it belong in. And the challenging thing here is, well, it does look like there's maybe a clear trend in some of these as it goes and approaches failure. It's tough to say, when does it cross this boundary? When does it go from one class to the other? Because it's kind of a thick bar as we move from left to right. So this is where we're going to bring in machine learning again. And I'm actually going to bring up an app to help us. So MATLAB has a number of apps that come with its various toolboxes, and you can also build yourself, for solving many different types of common problems, like machine learning, neural networks, control system design, signal processing, image processing, computer vision, connecting with hardware, and so on. And I'm a big fan of the apps because they give us a really quick and easy way to set up our problems, try things out, and not all, but most of them then have the ability to automatically generate some MATLAB code for us so that we get the programmatic way to replicate what we just did interactively. In this case, I'm going to open up the Classification Learner app. This is for solving classification machine learning problems. We're going to start by importing a variable from our workspace. So you notice I've got my 14 sensors here. I've picked them all out as predictors. And then our last variable that we created, this is our response. So this is the urgent, short, medium, or long. We also need to determine how we're going to test our data. So the idea here is we have some historical data. We want to train this model on our desktop. But then eventually we want to take this model and we want to use it in the real world where it's going to get data, it's going to get inputs that it's never seen before and where we're not sure what the correct answer is. And we want some level of confidence in how accurate the predictions of our model are going to be on this data it's never seen before. So what we do is we take our historical data and we split it up into 2 groups. One group we call the training data, and this is the data that we use to teach our model, the relationships between inputs and outputs. The other data, we call that test or validation data, and we hold that aside. We essentially pretend it was future conditions we did not know about. Once we've trained our model, we take the test inputs, we feed it through the model to get a test prediction, and then we compare the testing prediction with the test data to get a sense for how well is the model going to work on inputs it's never seen before. Now, there's a couple different ways we might do this. For us, we're simply going to take a random 25% of the data, and we're going to hold that aside to test with, and the other 75% we'll train with. Okay, so now that we've got our data into the app, Now we can take a quick look at how some of these different variables relate to one another. We can do some manual feature selection by turning variables on and off. We can do principal components analysis and apply machine learning to the results. We can also just go ahead and pick out some machine learning algorithms to try. So most of the more common machine learning techniques are available here, and if I want to try out something like a medium-sized decision tree, we can pick that out and train it. And so this will tell me that overall it's about 65% accurate. If I want to try something else, like a linear discriminant, we can pick that out, and that doesn't do quite as well. It's about 51% accurate overall. And this is a really important part of a machine learning workflow. One of the most challenging things about machine learning is there's no way to know ahead of time what's going to be the best model for my data until I just try a bunch of them out and see. So this gives me a really easy way to pick through some pre-made options, or I can even open up the Advanced tab to try and fine-tune them myself. And since I've run this before, I know that in this particular case, a k-nearest neighbor's algorithm is what will get us the best result. But again, there's no way to know that until you just try a bunch of them out and see. Now, there's many different ways we might evaluate accuracy here. The most common is using what's called a confusion matrix. So a confusion matrix allows us to compare the predicted class on the horizontal with the true class on the vertical and see what's our accuracy, where are we getting right answers, and what different types of mistakes are we making. And we can compare different techniques with this. So here you can see when the correct answer is urgent, I'm correctly predicting it was urgent about 75% of the time using this medium decision tree. When the correct answer was urgent, I incorrectly predicted it was short. You can think of this like a false negative. I incorrectly predicted it was short about 24% of the time. When the correct answer was short, I was incorrectly predicting it was urgent. This is sort of like a false positive, about 3% of the time. So we can use this confusion matrix to compare not just overall accuracy, but the different types of mistakes that we're making between these different techniques. So there's a lot that we can do to try to improve the accuracy of our machine learning models, whether that's on the pre-processing, noise removal, and outlier removal side, whether we want to try to create additional features, additional signals for us to work with, or if we want to try out different machine learning models. Eventually we'll be happy with what we have, and let's say this is good enough for us today. In the end, I want to either take this model and export it back to my workspace so I can use it, or generate some MATLAB code. So this will actually generate a new MATLAB function for me that will take new training data that I want to use and will retrain the model for me. And you can see the command right here. So this is a huge time saver, being able to set things up interactively in the app and then have it just generate all the MATLAB code that I need. In this case, I was able to just kind of copy paste this over into my live script over here. So we'll retrain our k-nearest neighbors algorithm, and you can see the results down here. Now there's a little bit of randomization in the process of training a machine learning model, so you notice the results will change a little bit from run to run, but it should be generally the same. And so you can see in this case, when the correct answer is urgent, we are predicting it's urgent about 92% of the time. About 8% of the time, we're making some kind of mistake. Now, machine learning models, by default, will treat all of these different mistakes, all of these different ways of making errors, as all being equal. But that's rarely the case in the real world. For example, these urgent cases, this is where our equipment is in a really bad place. It is badly in need of maintenance, and we're running a high risk of having an unexpected failure. So this is potentially a much more expensive mistake to make than something like when it's actually long, predicting that it has a medium time until failure. So what we can do is specify what's called a cost matrix. So this allows us to specify what's the actual cost of making these different types of mistakes. So if some of these mistakes, like when it's urgent and I don't get that, are more costly than the others, I can increase their weight in this cost matrix, and when I retrain my model, it will now penalize those those types of mistakes even more. So let's retrain this model. All I have to do is give one additional argument telling it what the cost matrix is. Oh, there we go. And let me pop this out so we can get them side by side. So here on the left, this is the original result. And then on the right, this is the result of using the cost matrix. And so you can see we went from about 92% accurate to over 99% accurate in the urgent case, because I told the algorithm when it was training that these types of mistakes are very expensive to make. However, this does not come without a cost. You notice that in the case of the short algorithm, or excuse me, the short class, originally we were getting it right about 85-86% of the time. Now we're only getting it right about 68% of the time. So this isn't reducing the number of mistakes we make, it's shifting the mistakes to areas where it's less costly to make. But if the cost matrix we defined really represents what these different mistakes cost us, then this result on the right over here, this is going to really give us the best result, because this is not optimizing for the minimum number of mistakes, it's optimizing for the minimum cost of our mistakes, and that's what we're really interested in. So we can keep iterating on this. There's lots of other things we could do here to try to improve the accuracy of our models. But let's say this is good enough for today. The question now becomes, well, how can I take this outside of my desktop version of MATLAB and use it to actually make forecasts on my equipment as I get in new data? Well, there's actually a couple different ways we might do that. So MATLAB can do a lot of things. It can do a lot of math and algorithms, it can make visualizations, it can even do graphical interfaces. And I can deploy almost everything, about 99% of what you do with MATLAB and its toolboxes, through the MATLAB compiler. The MATLAB compiler is an add-on to MATLAB that will generate a wrapper to put around your MATLAB code and then compile that into a software library. Something like an executable or a C++ library, .NET assembly, jar file, Python library, and so on. And you can then take these libraries and you can use them wherever you would normally use them, but they're running MATLAB code behind the scenes. So you could take this, give it to your colleagues, run it wherever you like. You can run it on a desktop, run it on a server or the cloud. But since it's actually running MATLAB code under the hood, it will need access to something called MATLAB Runtime. So MATLAB Runtime, this is a freely distributable copy of the MATLAB engine that can run these MATLAB compiler-built components. So once you build this, both the component you build with MATLAB compiler and also the engine needed to run it are both licensing and royalty-free, and you can run them wherever you like. However, since it's just running MATLAB code against the MATLAB engine, this can really only work on hardware that could normally run MATLAB. So a second option, if I only care about the math, about the core algorithms, so I can use something called MATLAB Coder. MATLAB Coder does an actual C code translation process. It actually translates your MATLAB code into standalone ANSI C code. This supports a much smaller subset of MATLAB and its various toolboxes, but still supports a really wide array of a lot of the math and core algorithms. And you can take this C code and then do whatever you normally do with it, build it into libraries, even run it on embedded hardware on the device itself that could not normally run MATLAB. You can even connect them and do a combination of the two. Maybe take some of your algorithms like the pre-processing and the noise removal, generate C code and push those down to run on the device itself before you upload any data. And then once you upload the data to some central place like a server, then you can have the more computationally heavy algorithms like the machine learning running through MATLAB compiler on the central server infrastructure. So whether you want to take your MATLAB algorithms and you want to deploy them to something like server or cloud, or if you want to deploy them to the equipment itself, or if you want to do a combination of the two, there's tools in MATLAB to help you do this. So where do you go from here? Well, in addition to having a lot of free information available on our website, we also have very robust training and consulting offerings. Our training organization does both in-person and online classroom training, both on-site and at public locations. We also have self-paced online training. And our training covers all of the core workflow that we talked about today: importing, visualizing, processing data, doing machine learning, deploying MATLAB applications, and also many other topics. Our consultants are very experienced in this area, both in the core data analysis and modeling, and also in integrating MATLAB into other systems. A few key takeaways for today. Frequent maintenance and unexpected failures are a large cost in many industries, and MATLAB enables engineers and data scientists to quickly create, test, and implement predictive maintenance programs. In fact, we looked at 2 very different ways of doing it that we were quickly able to do today. And predictive maintenance, if we can get this right, can save a lot of money for equipment operators, can improve the reliability and safety of our equipment, and can even create new opportunities for services that equipment manufacturers can provide. So that's about it for me today. Thank you all for tuning in. If you haven't done so already, please enter any questions you may have in the Q&A panel. We're about to go offline for a few moments, compile those, and then we'll come back online and answer as many as we have time for. Thank you.